So then I think I'll just get started. Is that okay, Renate?
Yes, definitely. Yes.
Good.
I can't see any further questions.
Okay, so let me just put this on full screen. Okay, is that visible? I would guess so. All right, so let me get started with the object of a relativist's desire, and that is the metric.
Blank screen.
We can't see your screen.
You can't?
Black square. Now we can.
No, it's it.
No, okay, but now when I go
Full screen.
full screen, then I have a problem, huh? Let me try again.
A black square.
Weird.
If you share screen again and choose another.
Maybe I'll stop share and then do it again. Yeah, I was told that there is some sort of a problem with I think
So sharing the window, not the screen. Yeah, I
Sorry?
think that if you share the screen rather than the particular window, that might solve the problem.
I'm not sure what you mean, but let me just try. Okay.
Yeah.
No?
Blank.
Blank. Okay. Stupid. Okay, so what did you say? What should I do?
As you share screen, there, Zoom prompts you to choose between what you share. Rather than selecting a particular window, you can say share screen, share the whole screen.
Ah, okay. Where is that?
It should be immediately after you press the share screen button.
I didn't see anything, but let me try again.
Maybe do you mean share whole desktop?
Yeah.
I get this. Let's see. Portion of the screen. Computer audio. No, that's not it. Full screen and then. Okay. So as I said, I want to continue and talk about the more technical things about the description of gravitational waves. It's the easier part of the technical things, and that's the linearization. That's what Einstein called the first approximation, and that's what I want to talk about. The first thing that I want to spend some time on is the object of desire of every relativist, and that is the metric. So what is the metric? The metric is the thing that tells us about distances between points on a surface or in a space. This is important because the geometry of a surface, I'll talk here about surface, but everything goes for higher dimensional object also. The geometry of a surface is determined by the distances between its points. So if we know the geometry of a surface, then we know the distance between each of its points, and vice versa. So if we know the distances between all the points, then we know what the geometry of or the shape of that surface is. So if we are in the plane, and I have 3 points here, this point, this one, and this one, then I can always put a triangle, a flat triangle between these points, and everything is nice. But if I now take 3 points in the same distance, so let me indicate this by going up a little bit in 3-dimensional space, perpendicularly to the plane. And I now want to fit a different triangle, a larger triangle between these 3 points here. Then, as you probably can imagine, this triangle has to bend in order to get attached to these 3 points here. And so that means that suddenly now we still have a triangle, but because the triangle started out to be larger than the blue one, So the red one is larger than the blue one. The red one has to bend. It has to change its shape, and so you see that the size of an object and the distances of points within that object determine the shape of that object. And so that's why it is important to understand how you give and determine the distance between any 2 points on a surface or in a space. So if we are in the plane, then you all know that this is easy. So if I have 2 points here, this one and that one, they have a distance L between them. And in Cartesian coordinates, I can compute the length or the distance between the points simply by taking the differences in the coordinate values of the 2 points. So this point here has a coordinate x1, y1. This one has x2, y2. And delta x is x2 minus x1. Delta y is y2 minus y1. And I can compute L squared as delta x squared plus delta y squared. That's Pythagoras. Okay, so in Cartesian coordinates, that's not a problem. But if I stay in the plane, I take the same 2 points and I describe things in polar coordinates, then I already get a little bit of a problem. So here I have the same 2 points, same distance. The coordinates, the polar coordinates are operating, as you know, by taking lines from the origin through the points and then measuring the distance between the point and the origin. That gives you the radial coordinate. And then you measure the angle between the x-axis and that line that you have drawn, and that gives you the phi, the value of the phi coordinate. And so the difference in the phi coordinate between these 2 points here is the delta phi, that's this angle. And the difference in the radial coordinate is this distance here. So I have a delta r and I have a delta phi. How do I compute L from delta r and delta phi? Now, the way I can do this is, it's indicated here. I can look at r times delta phi. This is roughly, or well, this is the length of this arc. And then I can use something like Pythagoras, and I could compute delta L, I could compute L squared as delta r squared, which is also this distance here, plus r squared delta phi squared. But that's not exact. That's not exactly right, okay? In a similar way, I can do it here. I can take, and this r here, I should say, is the coordinate of this point, the radius of this point. I can also take this triangle, this one here and here, and I can compute L squared is delta r squared plus r squared delta phi squared, where I take the r value of this point. And so I get a formula that tells me that the distance squared between the 2 points is approximately equal to whatever Pythagoras gives me. It's not exactly the same because this here is an arc and not a line, okay? And so this formula is only approximate. And of course, when the points are close together, then it becomes more accurate, because then the radial values between this point and that point, which you have to plug in here, become more or less equal if the points are close together. And so it's no use to specify the distance between a finite or the distance between points that are actually a finite distance apart. You will have to do this in the limit when the points are close together. And in the limit, they are infinitesimally close together. And that means that instead of looking at coordinate differences, one looks at coordinates differentials. That's, you can think of differentials as being the distance of infinitesimally close points, or the difference in coordinate values of infinitesimally close points. So in general, we specify the length or the DL between any 2 points in terms of an expression like this. So you see, when I go back, you see that we have a delta r squared plus something times delta phi squared. And so this something here depends on the coordinates. And so that's why one generalizes this to this form where I have 2 arbitrary coordinates now. And I get an expression that is quadratic in the coordinate differentials, du squared, dv squared, but a general expression which is quadratic in those differentials would also have a mixed term du dv. And so an expression like this here is called the metric of a 2-dimensional surface. So there are some conditions that you have to impose on these functions that I do not want to go into detail. But this is the general expression. And in the special case of Cartesian coordinates, these functions here are just constant. This is 1, and this is 1, and this is 0. In the case of polar coordinates, this one is still 1, this is still 0, but this one here is actually u squared if you want. And so you have to live with the fact that these functions are actually functions and not only constants. So that's the important things that these coordinate differentials here, as I said, you can think of as the difference in coordinate values of infinitesimally close points. These metric coefficients, these functions g, GUU, GUV, and GVV, they depend on the points, as you can see in the case of the polar coordinates. They change when you change the coordinates. So when you go from Cartesian coordinates to the polar coordinates, you have seen that the expression that I wrote down changes from delta x squared plus delta y squared. It changes to dr squared plus r squared d phi squared. So that means that those functions change when you change your coordinate system. But the combination, and that is important, the combination of the functions and the coordinate differentials, this expression here, this remains the same when you change your coordinate system. So the combination dl squared remains the same. And that means that different looking expressions, there's an S missing, different looking expressions can describe the same geometry, as you see in terms of the polar coordinates and the Cartesian coordinates. It still is the plane, but it's expressed in different ways. And so let me just show you as an example, which I think you may already have seen, what happens when I take the metric in Cartesian coordinates. So now I write this in terms of the differentials. I have dl squared is dx squared plus dy squared. And I do the coordinate transformation from Cartesian to polar coordinates. So I have x is r cos phi, y is r sin phi, as you all know. I compute the differentials. That gives me that dx is cos phi dr when I take the derivative with respect to r, and I get minus r sin phi d phi. Similarly, dy is this expression here. And now I plug that into dl squared. I get dx squared plus dy squared is this expression squared plus this expression squared. You multiply out, you get a term cos squared dr squared from here plus sine squared dr squared, which is equal to dr squared. And similarly, the d phi squared terms combine and give you an r squared d phi squared. And the mixed terms give you from here r times sine phi cos phi dr d phi, and here you get with a minus sign. Here you get the same term with a plus sign, so they cancel, and so that's the result. So this means that the expression dx squared plus dy squared has the same information content as the expression dr squared plus r squared d phi squared. They are identical. It's the same object, dl squared, expressed in two different ways using two different coordinate systems. Okay, so that's what's called the invariance of a geometric object under coordinate transformation. It does not matter which coordinates you are using, as the geometric object is the same irrespective of how you describe it. And that's the main principle that underlies relativity. And I'm sure Jörg will say much more about this in his lectures on GR. I wanted to use this as the motivation to actually writing down the metric of relativity, which is a step now into higher dimensions. We now have not only two coordinates, we have four coordinates or four dimensions. Three of the dimensions are related to space, and one dimension is related to time. And time and space are treated almost identically in relativity. There is a difference, which you see in a second. If we take coordinates that correspond to Cartesian coordinates in the plane, then we take the Cartesian coordinates for the space dimensions x, y, and z, and we have a time coordinate t. They are combined usually into coordinates x0, x1, x2, and x3. And so I interchange between using x, y, z and x1, x2, x3, and x0. And the metric of the flat space that corresponds to the two-dimensional plane is given in this way. It's usually written the s squared and not the l squared. And then we have this expression, which is almost the same as the expression for the metric in the plane, except that we have different signs in front of the squares of the differential. And we have a c squared here. So the signs, that's what I mean with time and space are treated almost identical. X, y, and z here have a minus sign, and the time coordinate has a plus sign. This is a convention that I am using. Other people are using it the opposite one, where you have a minus sign here and you have plus in front of the dx, dy, and dz. I like this one. That's why I use this, because it singles out the time and treats the space as the important quantity and treats the space then with the minus. This c here is the speed of light. This comes in because of unit considerations. And in appropriate units, one can take the speed of light as equal to 1, which means that when you take the time unit as a second, then the appropriate spatial unit is a light second. That's the distance a light travels within 1 second. And if you use those units, then c is equal to 1. So we can write this ds squared in this form, where I'm using the Einstein convention, where I'm summing over repeated indices, one up and one down. And so I can encapsulate in this eta a b here those four signs. So this eta really you can think of as a matrix that is diagonal. It has a 1 in the upper right corner and then minuses down the diagonal. In general, if we are not in Minkowski space, if we have not a flat space, but a completely general curved space, then the metric becomes this form, GAB times dxa dxb. That's still the coordinate differentials. And the GAB are functions that depend on the coordinates. So this is the straightforward generalization from this form here, from 2 dimensions to 4 dimensions. We have to encode into this GAB here the fact that the time and space are treated differently in terms of the signs. And this is encoded by saying that the signature, that's a certain invariant that you can have for a matrix, that the signature of this matrix here is -2. That's the mathematical statement that says that if you diagonalize this matrix, you end up with a form like this. Okay, so that's the metric. And now the metric is not a God-given thing. The metric is determined by the matter in the space-time. And so this is again the Einstein equation. Now I have C is equal to 1, so I don't have the C to the 4 as I had in the previous talk, but I still have the same structure. I have the Einstein tensor here on the left-hand side, which describes the geometry in the form of its curvature or part of its curvature. And I have the energy momentum tensor here that describes the content of matter that is in the universe or in that in the space-time. So we have again the left side and the right side are equal. Part of the geometry is given by the energy and momentum properties of the matter. This GAB is called the Einstein tensor, and it has this form where I have still an abbreviation here, because if I would write out this expression, it would be too long. So the main part is this one. This is called the principal part of this expression, because it has second derivatives of the metric functions. This here is a part that is quadratic in first derivatives of the metric functions. But this one is a product of the metric itself. This is actually the inverse metric, and or the inverse matrix, I should say. And then this is combined with these second order derivatives of the metric functions. So the Einstein tensor then consists of or contains second partial derivatives of the metric functions. And then we have an equation that says that this expression here is equal to TAB. And this is why I said earlier, the Einstein equations are a set of nonlinear partial differential equations of second order. So second order because we have second order derivatives, nonlinear because we have the product here of G, inverse of G and G itself. And here we have a product of first derivatives. So it's a highly nonlinear differential equation. And the right-hand side, as I said, is the energy momentum tensor. It describes some aspects of the matter, namely the energy and the momentum aspects. And in order to specify this, you need to specify further properties of the matter. And for this, you need to use other physical theories like hydrodynamics, electrodynamics, plasma physics, magnetohydrodynamics, all kinds of things that you want to couple to the gravitational field. And in appropriate units that I'm using from now on, the G, which is the Newton's constant of gravitation, the G can also be put equal to 1. So from now on, the G is equal to 1, and the Einstein equation is GAB is 8 pi TAB. Again, there are conventions, different conventions where you have a minus sign here, but that's not essential because the signs, this is just conventions and easily dealt with. Well, in principle easy, but sometimes you're chasing minus signs like crazy. Okay, so as I said, the Einstein equation is highly nonlinear, and therefore it's very difficult to solve explicitly. And so what Einstein did, and what I will do now also, is I'll consider what's called the weak field approximation, which is that I look at a weak disturbance of a gravitational field. And so I look at a weak gravitational wave that moves through an otherwise flat space. So flat space, as I said here earlier, is given by this metric or by this matrix, this eta AB. And so I write the metric of that weak gravitational wave as the sum of this background. So that's the flat space. And then the flat space is disturbed or perturbed by something weak. And I write this weak thing as an epsilon here. This epsilon is a number that is considered so small that epsilon squared is roughly 0. So there is a precise mathematical way of how you deal with these weak field approximations. You take one parameter families of solutions and so on, and you take derivatives, but that's not essential. The main point here is that we are looking at a weak perturbation of the flat space, and in all the expressions that one encounters, one throws away terms that are quadratic in H, which means quadratic in epsilon and higher. So we take this expression for G and plug that into the Einstein equation for the moment with TAB equals 0. So we are looking at a matter-free universe. We are only looking at a disturbance in the gravitational field. And then we ignore all the higher terms in epsilon. And then we end up with an equation like this. This is the, you recognize here that this is the principal part of the Einstein tensor. It doesn't have this H with the second derivatives of the metric. It only has the first part, the first 4 terms, and it only has them in the form where we have the flat metric here, and then we have derivatives of the perturbation of H. Okay, and now I'm doing what people in relativity do. We take this metric and raise an index, which means that we are summing over those derivatives here, and so I get this expression here. You can think of these objects here, these partial C and partial D. These are just the partial derivatives with respect to X, Y, Z, and T. And this eta here is only non-zero when C and D are the same. So the object that we have here is really dt squared HAB minus dx squared HAB minus dy squared HAB minus dz squared HAB. And then we have these other terms that you can combine or expand and write down explicitly. But this here, as I was just indicating, this here is a wave operator. But unfortunately, this thing has 3 terms additionally. So we have a linear equation, that's obvious, for H. The dA is a derivative with respect to the coordinates, as I said. The problem with this equation here is that it does not have unique solutions. So it does have solutions, but they are not unique. If you want to specify, if you do specify initial data, you cannot predict what's happening in the future because there are many solutions that have the same initial data for this equation. So this means that mathematically, this equation does not make much sense. So as one says, it's not well posed. It doesn't have unique solutions. Physically, it means it's useless because you cannot make predictions. Okay, so the whole thing here is not useful, and you have to come up with something else. So you need more information, and the information that we are going to use will eliminate these 3 terms here. Okay, so let me remind you of something similar in electrodynamics, which I hope most of you have already seen. So in electrodynamics, you know that we have the electric and the magnetic field, and we can write the electric field as in terms of potentials in this way, and the magnetic field in terms of the vector potential, where we take the curl of the vector potential, and the electric field is given by the negative gradient of the scalar potential and the time derivative of the vector potential. So given an E and a B, we can find a phi and an A, and such that this here is true. That's the statement of 1 of 2 of the Maxwell equations. But we also find that these potentials are not uniquely determined. Okay, so if I have a phi and an A that give me E and B, then I can do a transformation of this form where I add to phi a time derivative of a function, and I add to A the gradient of that same function, or in terms of these combined equations with indices, I can just say that where A0 is phi, the potential here gets added a derivatives of an arbitrary function lambda. So if I plug in the potentials for E and B into one of the Maxwell equations, then I end up with this equation here. And I see that I have this operation here, this dA, which is the wave operator or the wave expression acting on the potential. But I have an additional term that spoils the entire equation, and that has this form. It's the derivative of the divergence of this A. And now, because the potentials are not uniquely determined, I can now impose a condition on the potentials, a gauge condition, as it is said, which gets rid of this term. So I can impose what's called the Lorentz gauge, which says that the potentials have to be chosen to be divergence-free, so that this equation here holds. And one needs to show that you can actually always find a function lambda such that this equation here can be satisfied, which I'm not going to go through the details, but you can show this. And so there is always a function lambda such that you can satisfy the Lorentz gauge. And that means that in this equation, this unwanted term here drops out. And so we are left then with the equation that that's dA on AB. So this object here, which is really, when written out, the wave equation on the four potentials, is equal to 0. So that means that if we use the fact that things are not determined uniquely, the potentials are not determined uniquely, we can come up with conditions that eliminate unwanted terms in the equation. And then we get to the wave equation that we want. So you recall that I had these three terms here. And now we need to think about what we know about H and the metric in general, whether the metric is uniquely determined or not. So as I mentioned at the beginning, the metric does not change when the metric as a geometric object does not change when you change coordinates, but the functions, the GAB, they change when you change coordinates. And so that means that also here, this H here changes when you change the coordinates. And there's a particular way this H here changes when you change your coordinates, and that is in this way. So H changes by allowing a addition of this form, of a term of this form. And these x's here are four arbitrary functions. They give you a vector field on the space-time, and this vector field is what's called an infinitesimal coordinate transformation. So the H changes, only parts of the H are fixed, other parts can be changed in this way by adding a term of this form. This H that we start out with and the changed H, they describe the same physical situation. That's why one calls this transformation here a gauge transformation. And so we can try to use the fact that the H is not uniquely fixed, or we can have different H's that describe the same situation to get rid of those terms, those red terms in the equation. So the terms were of this form. One or two of the terms had an expression like this, and the fourth term had an expression like this. So if we can put those equal to 0, then those terms drop out. And those two conditions here are called the transverse traceless gauge. one can show that you can always find 4 functions x such that the transformed metric, this h twiddle here, actually does satisfy those two equations. That's again quite involved to get through this this statement that I just made. That's why I will skip it. This is something that one needs to do in detail and slowly, because there is some arguments involved that have to do with properties of PDEs and so on. But one can always find an H such that these two conditions here are satisfied. And then these conditions have 2 consequences. One is that they simplify the form of the metric. So this condition here says that you can make these entries in the matrix here 0. And that condition here says that the trace is equal to 0. And that means that the sum of the, the eta sum of the diagonal is equal to 0. That means that H0, 0 is equal to the sum of these 3 diagonal elements here. So that's this condition here. This equation here is the same as this one. Okay, so upshot is that we can always, by imposing the transverse traceless gauge, we can we find a metric that has this form with this condition, and then the equations also simplify, because you see here that's the transverse, that's the DC HCB is equal to 0 condition. This drops out, this drops out. This here is the trace condition. This drops out. And so we end up with an equation that is only this term here is equal to 0. And that is this term written out is the wave equation on those components of HAB. So we have a wave equation for the perturbation of the metric, for the metric components HAB. And now the wave equation is probably the most the best understood equation in mathematics or in PDEs, and it is always well posed. So you can always use it to predict things. Okay, now we do physics stuff. So we have the wave equation, and we make a plane wave ansatz. That means that I write the HAB in this form. I have an HAB hat that depends on K, and K is a vector that, well, I write this as e to the I k kx, which when you write this out is this expression here. So we are doing some sort of a Fourier transform if you want. Okay, so we take this ansatz, plug it into the equation. That means I have to compute the derivative of this function here. With each derivative, I get a factor I times k from the exponential. And so the first derivative has ik times h. Second derivative has ik squared, so that's minus kk times the function. And then I have to take the trace of this. So I have to take this with, multiply this with eta, and then I get this expression here, kc. I also need to put this ansatz into the gauge condition, this one, and that tells me that kc times this h hat here is equal to 0. Okay, so I get, from plugging this into the wave equation and into the gauge condition, I get 2 conditions for k in relation to h. That's those 2. The first one here says that k, the product of k with itself, is 0. This is the product in the sense of the Minkowski metric. And so that means that this is k0 squared minus k1 squared minus k2 squared minus k3 squared is equal to 0. And that means, in the speak of relativity, that this vector k here is a light-like or a null vector. So that means it lies on the light cone, and the light cone is the cone of all events that connect one event with another event. Sorry, it's the set of all events that can be connected by a light signal. And so this means that k is a light-like vector. It means that the wave speed of the wave is the speed of light. And the gauge condition here says that k times h is equal to 0. This means that when you look at this equation in detail, what this means, it means that the perturbation, I mean, when you write it out, it means the perturbation in the direction of k vanishes. And so the h only has components transverse or perpendicular to k. And that means that this is a transverse wave. So we find that the wave propagates with the speed of light, and it is a transverse wave. The two of the things that I mentioned in my previous talk. So now let's specify the direction in which the wave propagates. Namely, we want this to propagate in the z direction. That means that this vector k here can be written in this form, omega times 1, 0, 0, minus 1, because then in the exponential you get e to the I omega and then t minus z. And that is what you probably know characterizes a wave that propagates along the z direction. So we specify k to be of this form. And then the gauge condition says that the h must have this form where you only have 4 non-zero components inside here. So that's the x and y components, or 1, 2 components. And the t and z components are all 0. This is the fact that that h is transverse to the z direction. So there are no components here that combine z and x and z and y here, or z with z. Recall that this was 0 anyway because of the gauge condition earlier. Okay, and so we have those 4 entries here into the matrix. There is still the condition that the trace of this thing here must be 0. That means that H11 and H22 must add up to 0. The matrix is symmetric, which I've indicated here already by saying that this is the same element. And so there are really only 2 numbers in this matrix, because H11 is equal to minus H22, and those 2 are equal. Okay, and so if I only concentrate now on this 2 by 2 part here in the metric, then I can write it in this form, where I have an H plus, that is the corresponds to the H11 here, times the matrix 1, 0, 0, minus 1. That satisfies the fact that the sum of the diagonal elements is 0. And I have another matrix which has a factor H cross in front of it, which has 0, 1, 1, 0. That's when those 2 elements here are excited. And so I can write the entire metric here in this form as a linear combination of these 2 matrices. And, and this corresponds to those 2 polarization states that I talked about earlier. This one here gives you the plus component, or the plus polarization, and this gives you the cross polarization. It comes from this matrix here. And so we have found a plane wave solution which has a specified fixed frequencies. We have fixed the propagation direction. We have arbitrary amplitudes and phases, A plus, A cross, phi plus, and phi cross in the transverse direction. And so I can write that particular plane wave that I have found. Instead of e to the I kx, I can write this explicitly now in this form, where I write the h, the non-zero, the non-trivial part of h, in this form, where I have a sine of the given frequency and then t minus z, because it propagates along the z direction with an arbitrary phase and an arbitrary amplitude. And this gives me the plus part, and then I have a similar part for the cross. Okay, so I have a linear combination of those two polarizations with arbitrary amplitudes and phases. A general solution, obviously, is a linear combination of all plane waves with arbitrary frequencies and arbitrary propagation direction and arbitrary amplitudes and so on. And one can write this in this form where we are integrate. So n here is the direction of propagation. This is a unit vector, so it's only two-dimensional. Then we have the frequency here that we are integrating over. And then we have, I go back to the e to the I omega notation here. I write the exponent here in this way, t minus n dot x. And then this A here is a 2x2 matrix, or really a 4x4 matrix, but the essential parts are in the 2x2 direction, which depends on the direction in which the wave is traveling, and it depends on the two polarization states. So M can be plus or cross. So that's the general expression for a metric perturbation that is traveling in an empty flat space. So this is yeah. So that's the general solution of this homogeneous wave equation. In the next part, I will look at the generation of linear gravitational waves. So I look at the inhomogeneous equation. So for this, you have to go back to all the way back to essentially to here. You do the linearization, and then instead of having a zero here, you get something that depends on the energy momentum tensor. And once you go through the gauge considerations and all that, you find that the equation that you're looking at has this form. So it's the wave operator on H is equal to 16 pi times the energy momentum tensor, where H is transverse, so it satisfies this condition as before. But we cannot now necessarily make it traceless. So this thing here cannot be made, cannot be imposed, because this would impose a condition on the energy momentum tensor, which one does not want. So I'm lying to you here. This H is not the H that we started out with. There is some massaging in this. And this is what I indicated earlier in Einstein's paper. He had this prime on this gamma, and that's the same transformation that one needs to do in order to get the equation in this form. But this is not really essential. So I'm skipping this. So as I said, this condition here would impose a condition on the energy momentum tensor. But you may ask, doesn't this condition here also impose a condition on the energy momentum tensor? And the answer is yes, it does. The transverse gauge is only possible, so this equation here is only possible if the energy momentum tensor satisfies this equation here. But every self-respecting energy momentum tensor satisfies this identically, because this is the expression of local energy and momentum conservation. So every serious matter distribution that is physically reasonable must satisfy this condition. Otherwise, it's not a physical energy momentum tensor, and so then this does not make sense. And why would you want to couple? Why would gravity want to couple to something that is not a true matter distribution? Okay, so now we have a inhomogeneous wave equation of this form. And you probably all know that you can solve this by what's called a retarded integral. It's this expression here. If you do not know it, and I do not have the time to explain where this is coming from, this is dealt with in lectures on electrodynamics. So the solution of the wave equation with a source has this form. You see this weird combination here, t minus x prime. This is what's called the retardation effect. So the idea is that we are looking at the field at a time t and a location x, and the field is expressed by what the source did at some retarded time t minus x prime. X minus x prime is the distance between the location where we look at the field and what the source does at this location x prime. And so this here is the effect that it takes some information to travel from x prime to x. So that's why we have this retardation thing here. And then we have the fact that there is a 1 over x minus x prime here, and we have to integrate over the entire source region. That's the integration over x prime. So that's the general solution of this inhomogeneous wave equation. And now for the metric perturbation, we have several of those. And so we do this, we write down these integrals component-wise. So the 1,1 component here is given by the retarded integral of the t11 component here. So you have to think of this here as being component by component, we compute these retarded integrals. In order to see a little bit better what follows, I do a coordinate transformation between x prime and x minus x prime. So I call x plus z is equal to x prime, and I integrate over z. That makes this thing here a little bit easier. Okay, so I have this expression for the general solution of the inhomogeneous wave equation for the metric perturbation in Minkowski space. Now I do a Fourier transform in time, which means I write this h in this form. This is again, it's an HIB hat, and then I only do the transformation in time with e to the minus omega t, and I integrate over omega. That's the usual Fourier transform. I plug that into the solution and into the gauge condition again. When I do this into the solution, I find that I get this retarded integral, or this integral for the Fourier transform. And the gauge condition tells me that this must be true. That means that I can get this component, this h hat 0b for arbitrary b's, I get from the derivative of these components. And so these are components that contain a 0. And so all those components with a 0 are determined by the components with where the b is a spatial component, 1, 2, or 3. And so this means that I can concentrate on the spatial part of this HIB, but again, that's not that essential. So now I want to look at what is usually done also in electrodynamics. You look at the radiation zone or the far zone, which means that the distance between the location where we look at the field and the source is much larger than the 1 over omega corresponds to the wavelength, essentially. And then we have that this expression here, those two expressions are almost the same. And I can, in this integral that I have in here, I have e to the I omega z divided by z. I can replace this by x, the z by x, and then I can pull it out of the integral. So that's what I'm doing here. So I can write this h hat as e to the I omega x over x times the integral over the components of the energy momentum tensor. Now, And now this, the next step is something that, yeah, you need to stare at for a while. You recall that the energy momentum tensor satisfies the local energy momentum conservation, which means that it's a divergence-free quantity. So the derivative of the t, if I take the indices up, the derivative over the t is equal to 0 when I sum over these. So this, the energy momentum tensor satisfies this equation. And when I write this out, this means that I have this equation here, simply writing out the sum here. And then this means that I can write this as the time derivative of the Z0 component and the spatial derivatives of the ZK with ZK. So this means that when I have the time derivative of something with a 0, I can replace this with the space derivatives of something with space indices. And one uses this identity twice in this expression here in order to rewrite this object here or express this in terms of the set itself. So this is something that one needs to go through slowly. It is an identity that follows from this expression here. It looks complicated. It is complicated in a way, but it simplifies things in the end. You see here I have a dt with a Z0 and something. I can replace this with dk and the zk0 then, that's this term, and then I do this again. And then I rewrite this expression in this way so that I end up with the zk here. And so this means that I can, if I use this identity, I use the energy momentum tensor as the z here, and then I plug that into this integral. Then those two terms, these are total derivatives, those drop out when I do the integral. And so I find that the integral of the t, which is the integral corresponding here to the integral over z, is equal to the integral over the second derivative of the t00 times some x's, okay? And that's the result that I want to get at. So I rewrite this integral here as an integral over the 0,0 component of the energy momentum tensor multiplied with spatial axes. So this is x, y, and z, depending on what k and l here are. Okay. Now, the T00 in the energy momentum tensor is the energy density. So that's the density of the energy that the matter contains. And this expression here is has a name because it's important. This is called the quadrupole moment. So this integral up to a factor 3 is called the quadrupole moment. And this is almost the same as, this was wrong. This, instead of the omega, this should be a t. This is almost the same as what you know as the moment of inertia of a matter distribution. It's almost because, you know, in relativity, it's the energy density, but but mass is also energy. And so the mass density is also included in there. And if we are thinking of the T00 as only the mass density, then this is the moment of inertia, or the moments of inertia, depending on which one you want to compute. And so the quadrupole moment is very much related to the moment of inertia, except that it contains not only the mass here, but also the other forms of energy. Okay, so that's the quadrupole moment. And now with all these definitions and transformations, I can now write the metric perturbation in the far zone in the frequency domain in this way. Okay, so it's essentially given by the quadrupole moment, which depends on omega because I'm in the frequency domain. If I undo the Fourier transform that I did earlier, then I get this formula, namely that the metric perturbation in the far zone, which means far away from the source in the time domain, is given by this expression. And so this is the metric perturbation at time t, location x, is equal to the second derivative of the quadrupole moment of the source at the retarded time t minus x, or well, absolute value of x, you can think of r. So this is t minus r divided by r. So that's the formula that tells you what the metric perturbation looks like that is generated by a matter distribution. In the far zone, it's only the quadrupole moment that is relevant. You may know that in electrodynamics, in the far zone, it's the dipole moment of the charge distribution that is relevant. In relativity, it's the quadrupole moment. And it's the second derivative of the time derivative of the quadrupole moment that is relevant here. So this formula tells us several things. It tells us that the waves are caused by a change in the shape of the source. So this is what I had earlier with the rotating pen. If the pen rotates around its symmetry axis, then it doesn't change the shape, and then there is no gravitational wave generated. But if it rotates in an axis, in a different axis, then there is a change in the shape of the distribution, and that does generate a gravitational wave. So if the matter distribution pulses in a spherically symmetric way in time, so it grows and shrinks in a spherically symmetric way, which means it changes the monopole, then there is no consequence for gravitational waves. And similarly, if it changes the dipole by stretching in a direction or shrinking in a certain direction, there is no consequence. It's only created if there is a simultaneous shrinking in one direction and a growth or an extension in another direction. That changes the quadrupole, and that change of shape causes a gravitational wave. So we also see that as we go away from the source, this object here, the right-hand side, decreases by the absolute value of x, that you can think of as r, which is the distance to the source. And so the gravitational wave becomes weaker as you go further away from the source, very similar to electrodynamics, which also has this decay with 1 over r with the distance. Again, the gravitational waves propagate along the light cone. This is encapsulated in this expression here, t minus r. That is the fact that the c that is sitting in front of the t here is 1, means that this is propagating with the speed of light. And we also see that the size, the strain, the change in the metric, which is the strain here, is proportional to the second time derivative. If we wanted to compute, which I'm not going to do because this is really very complicated already on this level, to compute the power that is emitted by a source, then we would find that the power is proportional to the third time derivative of the quadrupole moment. And this is the famous quadrupole formula that Einstein wrote down. So I think I'm at the end of this part. I hope it was not too overwhelming, but most of the things are just basic physics things where you look at retarded integrals, Fourier transforms, and all that stuff. I hope I also have given you an idea where these statements are coming from that people are making about the gravitational waves. So with this, I'll stop, and we can discuss whatever questions you have.
Thank you very much, Jörg. It was very, very informative and gave us quite a lot of insight. Thank you. Any questions for Jörg?